Are you struggling to conceive? You have options, and at Piedmont Reproductive Endocrinology Group, we'll make sure you have the guidance and support you need. PREG is known for individualized fertility care that's unique to every patient. We take the time to provide a reassuring and empowering experience because we believe that you deserve nothing less. Let us help you on your journey to parenthood. Visit us at pregonline.com to learn more. Get the guidance and support you need at Piedmont Reproductive Endocrinology Group.
Hi there. Thanks for joining us. My name is Andrew Dunkley, the host of Space Nuts. It's good to have your company on yet another episode. Now, coming up on this episode, we'll catch up with Professor Fred Watson, strangely enough, because he's not in Australia at the moment. He's somewhere on the other side of the world talking to very important people, like his family, yes, and a few others from the United Nations, just by the by. So we'll be talking about what he's doing over there, but we'll also be focusing a lot of attention on audience questions this week, being episode 340. Is there a source of dark energy that may well now be defined? If it is, it's huge news. Rubble asteroid questions, magnetism, the mass of photons, artificial gravity, nuclear fusion, it's all coming up, and Fred hasn't pre-heard them. We're doing a potluck episode on Space Nuts today. Hope you can stick around.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And the man of the hour, or the man who is joining us for this hour, one or the other, is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Very good to see you again down there in sunny Dublin.
It's been very sunny. You're lucky to be in Scotland because we've just come out of a heat wave. Temperatures for about 4, 5, 6 days in a row up around the 38 mark Celsius-wise. Yeah, well above the 100 in the old scale. So we got a very, very significant change through on Thursday night that caused a bit of a problem around the coast, yes. Sydney included.
I know, yes. Heard about that.
Yeah, we got a dust storm. I was taking a photo of the dust as it rose up around town as the southerly buster, as we call them, blew through. And I actually snapped the camera at the exact moment of a lightning bolt. So I got a photo of a lightning bolt. Yeah, it was pretty cool.
I look forward to seeing that.
Yeah, I'll send it to you. But it's been very warm, but not so where you are.
If you take off the 30 from your temperature, that's about what we've got here. So I'm in Bonnie, Scotland at the moment. As you said, I'm visiting my family, albeit briefly, but I'm visiting my family, which is a delight.
Very nice.
Yeah.
But preceding that, you've spent a couple of weeks talking to people from... is it COPUS?
Yes.
The United Nations committee that is looking at the peaceful uses of outer space.
That's correct. So this is United Nations 101. United Nations has, as one of its offices, something called UNUSA, which stands for the United Nations Office of Outer Space Affairs. And within UNUSA is a committee, which is the Committee on the Peaceful Uses of Outer Space, or COPUOS. And COPUOS has a subcommittee, which is called the Scientific and Technical Subcommittee, and that is what I was at. So the last 2 weeks, the first 2 weeks in February, there was the annual meeting of the Science and Technical Subcommittee of COPUOS, and this was my first experience of being in that meeting. I was part of Australia's delegation, a small delegation of Australians attending, and I was there as an expert advisor on dark and quiet skies, which of course are very big in the hearts of astronomers. I did say it was my first meeting. That's not quite true because I attended quite a lot of COPUOS virtually last year. But it's certainly the first time I was there in person. The first time I could see the interaction between the different nationalities, the different nations represented by COPUOS, and also the first time I could see the process of how you achieve consensus among a very disparate group of nations with different ideas. I had the great privilege of presenting Australia's position on dark and quiet skies, which is essentially something to the effect that we recognise that, space, in particular, the idea of satellite constellations for internet access on Earth, that space is very important, that these satellite constellations are an important aspect of our future human life. But at the same time, Australia has invested considerable amounts in astronomical infrastructure and doesn't want space constellations to get in the way. And so that's really the nub of the issue, this balance between what the space industry wants and what we want from the space industry and what we want to protect in terms of dark and quiet skies. And my view is pretty optimistic about this, especially as we see the industry itself responding to the concerns of astronomers. So that was what took up a lot of my time during the 2 weeks of the Copperworth subcommittee meeting last week and the week before.
Yeah, I thought when it sort of focused on peaceful use,
yep.
They were going to be discussing, not putting weaponry in space. That's not part of it?
Yes and no. It's part of the assumption, the underlying assumption of the discussions of this committee that it would all be about peaceful uses. So
Gotcha.
Setting aside the possible military uses of outer space, which are a very different thing. But I have to say that idea did raise its head several times during the committee, but the committee is all about the peaceful uses of outer space.
I suppose with Vladimir Putin announcing that they're willing to ditch the nuclear non-proliferation treaty in the wake of the US support for Ukraine, that space would come into play as a potential launching ground, if you like. So, it's a hot topic.
Yeah.
But the peaceful use of space, we've got a lot more private entities getting up there, and it's getting very busy, as we've said before.
That's right, and that's the concern. That's the real concern about this of this committee, despite the fact that shadow that you just mentioned certainly cast itself over the committee and its deliberations.
I'm sure it did.
Yeah.
Yes, it certainly made big news around here. All right, and it's not over. You've got more work to do before you get back home, haven't you?
Yes, indeed. There's a conference on a much more scientific level. There is a conference which is all about the future use of surveys, big surveys in astronomy, and in particular coordinating optical surveys, invisible line, with the European Southern Observatory being one of the hosts of this meeting, and the radio surveys with the Square Kilometre Array Observatory being the other host. By the way, just incidentally, I briefly passed by the headquarters of the Square Kilometre Array Observatory yesterday at Jodrell Bank in the north of England.
Oh, wow.
Yeah.
Fantastic.
I didn't go in and say I'm the astronomer at large or anything. I went and had a cup of coffee instead.
Yeah. It's an amazing facility, though.
That's
spectacular.
Right. Yes, it is. Jodrell Bank is spectacular. That's true.
Now, Fred, we were going to discuss this breaking news, I suppose. It certainly caught my attention over the last few days, and that is the potential for the discovery of a source for dark energy. But it's also been brought up in a question. So I think we might go straight to the question, then you and I can discuss it after that. This one comes from Daniel.
Hi, Andrew and Fred. This is Daniel from Adelaide. I have a theory that brings together all of your favourite topics. Could black holes be the source for dark matter and dark energy? Could black holes suck up normal matter and energy and somehow convert them to dark matter and dark energy and then spit them back out? There's theories like Hawking radiation and the information paradox, which talk about how things can get out of a black hole, but they've never been observed. And maybe it's because they relate to dark matter and dark energy, which we also haven't observed. And here's why I think this could be a thing. So for dark matter, when it gets spit out, it could be gravitationally bound to the black hole and not go very far. And we already know that dark matter clumps in galaxies and around black holes. For dark energy, perhaps it gets spit out faster than light, which is why it can escape the black hole's gravitational pull, and could be why it's expanding the universe. And it's accelerating because as more and more black holes are created, more dark energy is being released. And for both, perhaps being faster than light is why we can't observe them. This is no doubt a crazy theory that won't stand the Fred test, but just wanted to ask the question. Love the show, guys. Thanks.
Thanks, Daniel. Well, interestingly enough, what you have just theorized may well be true. So there's a Nobel Prize headed your way.
Yes, keep an eye on the on your letterbox because that's the way it's sure to arrive. Great stuff, Daniel. And you are, in a sense, ahead of the curve there because for the first time, we've seen this week a paper, a scientific paper that exactly does that, links black holes with dark energy, not with dark matter, but with dark energy. Now, what is different from the Daniel theory is the mechanism for this. It doesn't involve things being spat out of black holes at the speed of light or anything of that kind. It's simply an observation that has been made that turns out to give you a possible explanation for the dark energy that we believe fills the universe and is causing the universe to expand ever more rapidly. And it comes about by a series of observations made by quite a large team of 17 researchers, 9 countries, led by the University of Hawaii, but including British scientists as well, which look at the way black holes evolve over time. And what they've done is they've looked at black holes which are in the early universe. So that what we do is look out to very distant galaxies and look at these black holes in the early universe. We can see how energetic they are and, how much they're gobbling up material around them. But then to look much later in the universe, in other words, to more recent times, to look at galaxies that we believe have run out of the fuel that would provide the black hole with, the meals it requires. That's the stars and gas that would surround the black hole itself and actually cause the black hole to increase in mass and become energetic. So the bottom line with this is that those recent observations of black holes as we see them recently, and these are all supermassive black holes in the centers of galaxies, they are much bigger than they ought to be. They're something like up to 20 times more massive than you would expect them to be just from the idea of these black holes accreting or gobbling up material. So that is something that you can't explain. The fact that they're up to 20 times larger than they were in the early universe, the equivalent types of galaxies, you can't explain by what you might call normal astrophysical processes. That's to say, the accretion. And what these scientists are drawing from that observation is that there is some connection, and it's being called cosmological coupling. There is some connection between the black hole itself and what's called its vacuum energy. Vacuum energy being essentially the energy of space itself. So what they're saying is that black holes themselves generate an energy that is somehow coupled to the expansion of the universe, so that this energy increases in mass as the universe expands, and that maybe that is the source of dark energy. And in fact, the reason why they make that link is that the idea of this coupled energy from black holes going into the universe itself, actually, when you do the calculations as to how much vacuum energy there should be in a black hole, and look at the accelerated expansion of the universe, you get the same answer. So the black holes can provide the energy required for the universe's expansion to accelerate. And that's the bottom line with this work. I'm going to say a little bit from the study's first author, Duncan Farrer of the University of Hawaii. He is somebody who used to be at Imperial College in London. We can quote what he said. He says, "We are really saying two things at once, that there is evidence the typical black hole solutions don't work for you on long, long timescales. and we have the first proposed astrophysical source for dark energy. What that means, though, is not that other people haven't proposed sources for dark energy, but that this is the first observational paper where we're not adding anything new to the universe as a source for dark energy. Black holes in Einstein's theory of gravity are the dark energy. In other words, if I can put that in a different way, we don't need to look at unusual sources of energy that might be making the universe expand more rapidly. It is actually coming from the black holes themselves, which we understand at least at some level. This, I think, potentially is extremely exciting, Andrew. You and I have talked many, many times about both black holes and the dark energy. But to link them together may well be something that might result one day in a Nobel Prize. Watch this space.
Yeah, what's your letterbox, Daniel?
Yes.
You said it first. But I guess the hard part is, how do you prove it?
Yeah, so you've got to, in a sense, this is laying down the first layer of proof, because this comes from observations. The fact that when you observe black holes in the early universe, black holes in today's universe, there is a mismatch in what you expect their masses to be, that they are up to 20 times more massive than what they should be if all they're doing is accreting material. And so that is a really interesting step. Now, my expectation, Andrew, is that this will be challenged by other astrophysicists, and we might see a bit of detail in the challenges that perhaps have been missed by these authors, but it's certainly a very interesting first step in perhaps a real understanding of what dark energy is all about.
Indeed, yeah, it'd be extraordinary. But it sort of prompts a question in my mind. If black holes are responsible for the production of dark energy, which is also responsible for the ever-increasing expansion and acceleration of the universe itself, when all the black holes die, will we have a Gnab Gib?
Maybe a Gnab Gib will, or the Big Crunch, as it's sometimes known. So that is a really good question. And my guess is the answer is no. And the reason for that is that, yes, black holes do evaporate because that's what Hawking radiation does. But they evaporate on hugely long timescales. And so I don't think you can wait that long because before then you might have had the big rip where the fabric of space itself is torn apart by the expansion of the universe.
There it is. All right. Just like blowing up a balloon. They eventually have a big rip. And my granddaughter Harry's going to be blowing up a lot of balloons today because she turns 4.
Oh, fantastic. Happy birthday, Harry.
And thank you, Daniel, for your insightful question. You've actually hit the nail on the head of some news that only came out in the last couple of days. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
And Marty Baker, the Eagle and Lambert.
You're listening to Space Nuts, the podcast about astronomy and space science with Andrew Dunkley and Professor Fred Watson.
Now, Fred, we might as well continue to load the audience with questions. We got when we appealed for more questions a few episodes past, we got inundated.
Excellent.
And some of them are sort of looking at things we've talked about recently, including Andrew.
Hello, Fred and Andrew. Great episode. I'm really enjoying the latest one, but I have paused it because I had a burning question after your item about the rubble pile asteroids and how long-lived they are. Very, very fascinating. I'm wondering what the different danger level is from rubble pile asteroids versus the solid ones. And just wondering, shouldn't a rubble pile asteroid burn up a lot more than a big one and thus potentially be less damaging? Anyway, fascinated to hear your answer to that one, and keep up the great work, guys. Thoroughly enjoy it. Been listening from the very early days. This is Andrew from Melbourne, by the way. Cheers. Bye-bye.
Thank you, Andrew. Hope you're avoiding those grass fires. That's another thing that's happening at the moment. Big grass fires around Victoria and north of Melbourne. So, yes, not a place at the moment. But yeah, good question. I mean, we talked about those rubble asteroids recently. We might recap on what they are, but I mean, in short, they're a conglomerate type of asteroid. But it turns out they're tough as nails.
That's right, and this work came from the Hayabusa spacecraft with the samples brought back from asteroid Ryugu, which, as we know, is a rubble pile asteroid. It's a pile of debris, and it was the careful analysis of crystals within those samples that gave rise to the idea that rubble pile asteroids last a lot longer than what you might call monolithic asteroids that are one chunk of material. That was the result of the isotope measurements and the crystallography. And the inference of that was that maybe they are harder to destroy, that they kind of behave in a springy fashion. If they're clouted by something else, they act like what you might call a giant space cushion. In fact, I think that's a quote from one of the authors of that paper. And so that giant space cushion takes a blow but doesn't destroy the rubble pile asteroid, which is exactly the opposite of what you would expect to happen. You'd think a pile of debris, you hit it with something else, would just fly apart, but that is apparently not the case. So the other inference from that was that perhaps because these asteroids may well be very long-lived, perhaps there are more of them than we expected. And the good news story as an aspect of this was that a rubble pile asteroid might well respond well to the shockwave of a nearby nuclear blast if you needed to detect one. And just going back, Andrew, to my time with the United Nations last week and the week before, I also had the great pleasure of sitting in on a meeting of the International Asteroid Warning Network, who think about exactly this sort of thing. And the rubble pile idea was one that certainly was discussed during this meeting, that you might be able to use an indirect nuclear blast to deflect one more readily than you could a monolithic one. Now, that doesn't answer Andrew's question, which is about how much does a rubble pile, disintegrate as it passes through the atmosphere. And my guess is that given the apparent resilience of these rubble piles, it may well be that they would still behave much the same way as a monolithic asteroid when they're heated to, high temperatures by their passage through the atmosphere. Of course, a big rubble pile asteroid would be an object of considerable danger to the Earth, because you're talking about something that could clearly generate probably statewide and maybe even continent-wide damage, depending on the size. I'm thinking now about things of the order of 100 meters across. I think, yes. So I haven't studied the details of this. I'm sure there are other people. In fact, some of the colleagues I was speaking to in the International Asteroid Warning Network might well have thoughts on this. But it's intuitively, I'd expect it would be bad news either way. That's the bottom line if something was inbound of that mass.
So, Andrew, if you hear of one heading towards Earth, don't go out without your umbrella.
I thought it was a paper bag you were supposed to take with you for things like that.
A bag on your head, probably as effective.
Yes, that's right.
Yes, indeed. But great to hear from you, Andrew. But the answer is, sorry, it's still going to kill us all.
Hopefully
the nuclear blast theory will fix it.
That's right.
All right, let's move on to our next question. This one comes from Peter.
Hello, I'm Peter from Iowa, United States. I just finished listening to an old episode called Magnetism that you guys did. And I was wondering, black holes, if photons can't leave the event horizon of a black hole, how do magnetic field lines get out? Doesn't quite make sense to me. Also, the second question, during the episode, Dr. Watson said that the magnetic north pole of the Earth was wandering around, and it was currently somewhere in Siberia. I always understood that the magnetic North Pole was in the southern geographic pole, that the magnetic north of your compass needle points toward the south, so that the south magnetic pole was actually the north geographic pole. If I got that wrong, thanks, guys. Great show.
All right. Thank you, Peter. What I want to know is whether he was turning left or right. I heard a car indicator in the background of that.
Depends which way the magnet was pointing, obviously.
Yes, indeed.
Yeah.
Which side of the road.
Yeah.
And so a double whammy, magnetic fields and how do magnetic fields escape the sun when its gravity is so very intense and everything falls back in? Is that what he meant?
Yeah, well, yes, I think he was specifically referring to black holes, though, as well, which also have magnetism. It's a good question, actually. The magnetic field around a black hole, is it escaping through the event horizon or not? Because magnetism is carried by photons, which are subatomic particles, the electromagnetic force carrier. And my guess is that the magnetism must be created outside the event horizon, but I'm not enough of a black hole specialist to know the answer to that. So I might defer to my colleagues about that. However, Peter's right about the magnetic pole. We conventionally refer to the north magnetic pole of the Earth as being the one that's in the northern hemisphere, even though it would be the south pole of the magnet that would point towards it in a magnetic compass. So you're right to pick up on that. And in fact, I think we had that debate at the time. But what we conventionally describe as the north magnetic pole is indeed in the northern hemisphere of the Earth, because it wouldn't make much sense if the south magnetic pole was up there among the ice.
It wouldn't really, would it?
No, quite so.
But what happens when the magnetic field of the Earth flips? Is that going to mess all that up?
Yes, well, that's right. It means that your magnet points the other way.
The way it should be.
I think we should all look forward to that when it might happen within the next 2,000 years or so.
Right, okay. Hold your breath.
Yes.
So the answer to your question, Peter, was don't know and yes.
That was it. Well, it's better than yes and don't know.
Good point. Good point. All right. Thanks, Peter. Great to hear from you. And we'll I suppose, as Fred said, we'll wait till the flip happens and then everything will be sorted out. This is Space Nuts.
0G, and I feel fine.
Space Nuts.
Now, this question that comes from Alan, Fred, you touched on in answering Peter's question. This is actually about photons.
Hi, Alan from Copenhagen, Denmark. I just learned from another podcast that photons carry no mass. Then how can they carry energy when E equals mc square? Hey.
Yes, indeed. That's a good question. Now, you talked about what photons carried in the previous answer. So if they've got no mass, how can they carry something? That's a good question.
What they don't have is what's called a rest mass, because you can't stop. Well, you can actually stop a photon, but that needs special sorts of equipment. But they don't have a rest mass, and so they do carry energy exactly in accordance with other equations, a bit like E equals mc squared. So photons carry electromagnetic energy, and indeed magnetism is a form of that, and so it's carried by photons, as we were just saying. But the deciding thing is clearly photons do have energy, and in fact, when we talk about the wavelength of light, for example, the smaller the wavelength, the higher the energy, and so when you get to things like gamma rays and X-rays, these very high energy photons, then we just discuss them in terms of their energy rather than talking about wavelengths or frequencies at all. It's just the amount of energy that photon carries. But the bottom line, Alan, and it's a great question, and it probably sounds like a glib answer, but it's that if you stopped a photon, it doesn't have mass. That's the bottom line.
Well, it's interesting you should say if you could stop a photon. I read an article the other day. There's I can't think of the scientist's name, but she's been playing with light.
Yeah.
And she's actually been successful in manipulating light
Yes.
and affecting photons. And she actually reduced the speed of light to 17 meters per second in a lab, which I just can't comprehend that. And she said she could even save it up and use it later.
Yes.
I can't get my head around that.
And neither can I. And I know these experiments take place, and they use they basically use sort of highly focused clusters of atomic nuclei to interact with the photons. It's a field that I don't know too much about, but it's a great area of physics. And you're quite right that you can slow down photons to have a speed of light that is very slow indeed. But I think it needs very special manipulation of the light beam by focusing, as I said, particles, subatomic particles, in such a way that they interact with the photon and slow it down.
I suppose those kinds of experiments and those kinds of achievements also help explain how light moves around the universe and how we can still see things that happened so long ago because of the manipulation of gravity and all the other things that are affecting the movement of light around the universe. So
that's correct.
And that's how you can see one thing happen 3 times because of the light moving at different speeds due to gravitational waves or gravitational effects and the lensing and all of those things.
It's quite about lensing. That's right. So it's you're quite right. Sometimes you get a phenomenon, a burst of energy from maybe a supernova explosion that takes different pathways around a galaxy whose mass is acting as a lens, and so you get perhaps 3 different images of the same thing. And there's been some remarkable work done on this kind of thing, including predicting when a supernova explosion will be seen. I think that's happened. And the prediction turned out to be correct because it had already been seen by a different pathway of light going around another object.
Indeed. All right. Thank you, Alan. Our next question comes from Robert. This is a bit of an old chestnut, but I love talking about this.
Hello, Fred and Andrew. This is Robert from Adelaide, small village near Amsterdam. Love the podcast. Really fun. Really interesting. Please keep making it. I have a question about artificial gravity, guys. How far along are we? Because it's really important for humanity to be able to go into interstellar space. Now we have this artificial gravity. I know you can take the centrifugal force, it'll push it down. Is that exactly the same as artificial gravity? Do we need a huge colossal ring in space to make this force happen for people so they can, healthily get to a very far destination? So that's my question. Thank you so much for taking time, and please keep doing what you're doing. Thank you.
We will try to keep doing what we're doing, which we're doing right now. But thank you, Robert. Artificial gravity, it comes up from time to time. It's there's a long way to go before we get there, I think.
Yes,
would be fair to say.
Although there is work on it, and I think I might have said this before to you, Andrew, on Space Nuts. We had a visit several years ago, it's about 4 years ago now, I think, from Linda Spilker, who was the Cassini project scientist, the Cassini spacecraft. And her husband runs a company that is working on artificial gravity solutions for spacecraft. And I think certainly when we spoke to him, Dr. Spilker, male Dr. Spilker rather than female Dr. Spilker, he had a contract with an agency usually known as NASA. He was kind of working a lot, in high-flying regions. And I had quite a long chat with him about artificial gravity caused by the acceleration because gravity, is equivalent to acceleration. We can generate an acceleration by having a rotating wheel, exactly as in 2001: A Space Odyssey, and the nuances of that are really interesting, in that there are only a certain range of rotational speeds for which you get something that simulates gravity without peculiar effects. If you have the thing rotating too quickly, or your wheel is too small, you're standing on the outer edge of this wheel with your artificial gravity. But it tends to produce rotational effects in your brain that cause nausea and have strange things like if you drop a coin or something, the coin doesn't go straight downwards, i.e. outwards radially. It goes off to the side. And that's very counterintuitive. But this was work that's ongoing. So it is actually a field of activity within the astronautical community. Just an aside here, which is straying way off Robert's question, but I think is really interesting. And again, this is a news item that came out this week. But we usually associate the idea of gravity and acceleration being equivalent with Einstein, because his equivalence principle was something that was, I think he realized that back in 1907. It was after he published the special theory of relativity in 1905, but before he got to the general theory in 1915. It may have been a little bit later than that, but he twigged this point that gravity and acceleration are equivalent. He called it the equivalence principle. And it turns out this recent research that has been done by scientists from a number of universities, including Caltech, the California Institute of Technology, that show that Leonardo da Vinci did an experiment that demonstrated the same thing. Really very clever, that Leonardo grasped the idea that there is an acceleration which is the equivalent of gravity. And I think that's an extraordinary thing for somebody to realize in the early 16th century. It's usually Galileo we think of as laying the groundwork of that equivalence, but it looks as though Leonardo got there first.
So Isaac Newton should have just eaten the apple.
I think he did, actually, in the end. You can follow this up, actually. There's a paper which is in a journal called Leonardo. It's called Leonardo da Vinci's Visualization of Gravity as a Form of Acceleration.
Yeah, he was way ahead of his time, wasn't he?
Certainly was.
Right. All right. This is Space Nuts, Andrew Dunkley with Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, we might squeeze in one or two more questions, Fred. This one, again, looks at something we've talked about before. This is Tom.
Hello, Fred and Andrew. This is Tom from Minnesota, and I just wanted to congratulate the two of you on being selected to be cryogenically frozen until nuclear fusion is ready to be integrated into space exploration. Now, when we thaw you guys out, you're going to have the honor of getting to pick where the first nuclear fusion-powered rocket is going to go, and I am so curious to hear what you think might be the goals of that first mission. Love the show. Thanks so much.
Thank you, Tom. Interesting way to ask a question. We've talked about long-haul travel in space and ways to propel ourselves, sails, light sails. We've talked about traditional rockets just not holding their water, so to speak. But nuclear fusion has been talked about as a potential way of traveling at pace, long distance in space, and that's what he's alluding to. So, and I know they're working on all sorts of options, Fred, and the time will come when they find a way to reach reasonable speeds, because that's the challenge, isn't it? Getting fast enough to get somewhere before we all, drop off the twig. But where would we go first? That is the question. And my first thought when I listened to Tom's question, my first thought would be Alpha Centauri. I mean, you go to the nearest star that's not the sun, would you not?
I think I actually think you'd be going even nearer than that. I think you'd try it out
Really?
first on the moon.
Oh, okay. Well, yeah, that would make
See how
sense.
quickly you can get there. It's really
No,
interesting.
I was
Sorry.
beyond the testing phase.
Yes, all right, beyond the testing phase. No, Tom's quite right. But you might be surprised, or you may not be surprised to hear this, Andrew, but there is a working group on nuclear power sources in space, which had several meetings during the COPUOS subcommittee meeting that I was at a couple of weeks ago. And that working group was chaired by a very eminent British physicist, somebody who's worked with nuclear power sources over many decades, Dr. Sam Harbison, who actually retired from the lead of the working group. But I sat in on some of those sessions. Really interesting, the kind of things that are being discussed in terms of nuclear power sources in space. And fusion, of course, is always the holy grail. My feeling was that nuclear fusion as a power source in space is not seen as the panacea that you might think it is. It doesn't solve all the problems. It just gives you a bit more of a string to your bow. But I'd be inclined to agree with you that if you did have a new form of energy, a new form of propulsion that was going to get you somewhere pretty quickly, then Alpha Centauri would definitely be a worthwhile target. It's still going to take you no fewer than 4.5 years to get there, because that's how long light takes to get there or to come back. But yeah, I think that's a pretty good guess, and I'd go along with you, Andrew.
Okay.
I hope Tom agrees.
Yes, and just keep working on your nuclear fusion generator, Tom, and let us know when it's done, and we'll take a look. I think we can just throw in one very quick question from a YouTube listener, Emil from Denmark, who follows us on YouTube. He said, I don't know if you ever read YouTube comments. Obviously, somebody did.
Yeah.
He said, but I've always wondered if the atmosphere of the Earth is hiding colours of space, like the effects from the sun, which seems yellow but is actually white, ? Also, how come gas is blue at 2,000, I'm assuming, degrees Kelvin, and the sun is yellow at 6,000, but you need 10,000 Kelvin to get a blue star? Hope life is good, and glad you're uploading to Spotify. I am too. Okay. So is the Earth's atmosphere hiding the true colours of the universe from us?
Yes, at some level it is. And exactly as Emil said, its effect is to redden light very slightly the scattering of the atmosphere removes the blue light from the atmosphere, so you get something redder. And the same's true with light passing through dust clouds in the distant universe. We can work out by how much reddening there is, how much dust there is around there. So there is this modification of colours. The second part of his question is very interesting. So that blue, a star like the sun, which is white, is at about 5,000 degrees Celsius, or Kelvin actually, which adds a further 273 degrees onto it. But a star like Sirius is indeed at a much higher temperature and looks bluish. But that's different from the blue of a gas flame at 2,000 degrees, which is glowing blue because of the emission of light from different gases within the flame. What you're seeing with the star is what's called black body radiation. It's as if the star was a completely black body, and you heat it to that particular temperature. That would be the color that it would be, and that's the same is true of the sun. So we're talking about two different physical processes there that are giving you two different sets of color and two different lots of blueness, if I can put it that way.
No. Okay. So a red dwarf would be what temperature?
2,300 thereabouts. Quite cool.
The lower the temperature, the redder.
Yes, exactly.
Higher the temperature.
That's exactly so. And in fact, we in the lighting industry, and you might know this because when you buy a light globe or a light bulb, you might find something called the correlated color temperature marked on it. And it's a temperature in degrees Kelvin, which is essentially a measure of the color of the light. So something like 3000 Kelvin would be a warm light. It would be almost yellow in color, whereas something at 5,000 or 6,000 Kelvin would be intensely white and have that almost painful whiteness about it that we sometimes see with LED headlines, for example, on cars.
Yeah, indeed. All right. Great question from you, Emil. Thank you so much for getting in touch with us, and hello to all our YouTube followers. We are pretty well done, Fred. I will remind people, if they do have questions, to send them to us via our website, spacenutspodcast.com or spacenuts.io. There are a couple of links there. You can, the AMA link at the top where you can send us text or audio questions, or the tab on the right that says send us your voice question. Don't forget to tell us who you are or where you're from, because we love to know. And that way you can get stalked by somebody who listens. No, nothing like that. But it's always good to know who we're talking to. And while you're online, don't forget to check out the Space Nuts shop on our website. And if you're interested in becoming a patron, you can look that up as well. And thank you to all our patrons who have been supporting Space Nuts for such a long time now. Your support is certainly welcome and greatly appreciated. Fred, we're done. Thank you so much from Bonnie, Scotland.
It's a great pleasure. Ochai the new, and thank you for fitting me in this week. Good to talk to you.
Thanks for finding the time, because I know it's it's been 11:30 your time now, isn't it?
Something like that. That's correct.
Yeah. And you're about to go to bed, and I've only just got up.
There you go.
But all right, we'll look forward to catching up with you soon, Fred. Thank you.
No problem, Andrew. Good to talk. See you next time.
Okay, Fred Watson, astronomer at large, part of the team here at Space Nuts, and thanks to Hugh in the studio, who didn't turn up today, but he'll turn up later and do all his editing and coffee making and everything else. From me, Andrew Dunkley, thanks for your company. We look forward to catching you again on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.